Have you ever wondered why the difference between a solid B grade and an elusive A star in Cambridge computer science often comes down to just a handful of very specific questions? I mean, what is it about interpreting complex binary representations that separates the good students from the absolute masters of the subject? Well, think about a world-class Olympic gymnast for a second. They don't just throw themselves into the air, spin around, and hope they land on their feet, right? Absolutely not. Every single twist, every rotation, every extension of their body is meticulously calculated. And the judges? They aren't just looking at that final pose. They are scoring the entire routine. They're looking for perfect form, the absolute precision of the execution, and of course, that flawless, graceful landing. In the Cambridge 96-18 AS and A-level computer science exam, you are that gymnast. And your routine? Well, it's how you handle assembly language bit operations, and, XOR, and OR. These questions are notoriously tricky, and today we are going to look at exactly what principal examiners are searching for in your answers, and how you can stick the perfect landing every single time you're faced with one.
Welcome to this explainer. I am incredibly thrilled to guide you through what is arguably one of the most critical, high-stakes topics in your entire syllabus. We are decoding the perfect form exam strategy specifically for assembly language bit operations. You see, the academic benchmarks for this topic require highly logical, structured reasoning. The Cambridge Assessment Framework actively prioritizes analytical depth over superficial breadth. You literally cannot just memorize what an AND gate or an XOR instruction does and expect top marks. It just doesn't work that way. You have to execute your knowledge with total precision. You need to show you're working, prove your methodology, and make sure every single sentence of your answer has a graceful landing. Let's dive right into this by looking at two very common yet entirely flawed approaches to a classic past paper question on bit operations. Imagine two students taking the exact same exam. First, we have Alex. Now, Alex knows the textbook inside and out, but their answer is absolutely overloaded with raw facts and has zero actual analysis. It's just a brain dump of everything they know about logic gates, completely ignoring what the question actually asked. Then we have Sam. Sam was clearly under immense time pressure. Sam rushed and completely missed the command word requirements, merely describing the operation instead of actually evaluating it like the question demanded. Both of these approaches result in a massacre of red pen marks from the examiner. Principal examiners specifically and consistently penalize these exact approaches because they completely lack analytical depth. They don't want to know that you've memorized the textbook, they want to see you apply it.
So how do we avoid the dreaded red pen? Here is our roadmap for today's explainer. First, we'll cover the core principles. Second, we'll go through a procedural framework to completely transform your answers. Third, we'll jump into a rapid-fire interactive workshop. And finally, we'll break down the critical examiner warnings you absolutely need to know. We are building a bulletproof system today, so let's get into it.
Section 1. Core Principles. Let's set the baseline. In Cambridge computer science, you absolutely must demonstrate a connected, conceptual understanding that transfers to totally unfamiliar contexts. The entire theoretical architecture of bit operations rests on precise definitions and causal relationships. We're talking about AND, XOR, and OR. Now here is a massive examiner alert, straight from the grading reports. Candidates consistently confuse these key terms. It happens all the time. You must precisely state your logic. For example, if you're using an AND operation, you need to explain its causal relationship with zeros. The fact that ANDing with a zero clears the bit. You have to prove your knowledge to the examiner through crystal clear, unambiguous definitions. If you use vague language, you will lose the mark, guaranteed.
And this right here is where we elevate your answer from a standard B grade to that A-star territory. This is cross-topic integration. Principal examiner reports continually highlight that candidates who reference cross-topic connections achieve significantly higher marks. It's all about seeing the bigger picture. Think about your earlier foundations from syllabus codes like 0417, 0478, or 2210. How do these AND, XOR, and OR operations connect to network subnet masking? Or what about pixel color manipulation and image processing? When you can show the examiner that you truly understand how a bitwise XOR is fundamental to cryptography, you are demonstrating real, undeniable analytical depth. You aren't just looking at one piece. You see the whole chessboard.
So, the absolutely crucial question is, how do we actually structure these brilliant insights on paper without creating a messy wall of text? Enter the Peel framework. Point, evidence, explanation, link. This is your safety net. This is your gymnast routine. First, point. State your main argument clearly right out of the gate. Second, evidence. Extract specific data from the binary representations actually given to you in the question. Third, explanation. Detail the causal relationship using those precise definitions we just discussed. And finally, link. Connect it all back to the specific context of the question or a broader cross-topic principle. Top students structure every single extended computer science answer this exact way. It is a total game changer. Before we continue, subscribe to our YouTube channel, Ace the Exams, at acetheexams_IGCS to excel in your Cambridge examinations. Click that subscribe button and hit the bell icon right now.
Section 2, the transformation. Let's look at the method mark strategy.
Now, in assembly language questions, the actual process of calculating the binary operations is just as vital as getting the final answer correct. Cambridge heavily awards method marks. So let's bring Alex and Sam back into the picture. If we take Alex's massive fact dump and apply the Peel framework to it, the transformation is incredible. Instead of rambling, we make a clear point about the XOR operation. We use evidence directly from the provided bit mask, we provide a solid explanation of how the bits toggle, and we link it firmly back to the system flags mentioned in the prompt. By explicitly showing the examiner your step-by-step methodology, those brutal red pen marks instantly transform into green check marks. You are literally guiding the examiner to give you points.
To ensure you can execute this flawlessly under intense exam pressure, you need to internalize this 5-step procedural framework. Step 1. Deconstruct the command word. Are you explaining, describing, or evaluating? Step 2. Extract the relevant binary data from the scenario. Step 3. Select your analytical framework. Remember, AND to clear, OR to set, or XOR to toggle. Step 4. Execute the operation with clear line-by-line notation to secure those method marks. Step 5. Present your final answer using the correct Peel terminology. This is your ultimate blueprint for success. Stop scrolling. Subscribe to our YouTube channel, Ace the Exams, at acetheexams_IGCSE to excel in your Cambridge examinations. We've helped thousands of students improve by 2 to 3 grade boundaries. Join them right now by subscribing to @acetheexams_IGCSE and turn on all notifications so you never miss our weekly exam strategy sessions.
Section 3, interactive workshop. It's time for the 60-second data scan challenge.
All right, your first challenge is the data scan. When you are confronted with a complex binary data table in the exam, you have to be able to extract the core trend incredibly fast. Correct data interpretation always happens in 3 distinct phases. First, you extract from the binary, isolating the exact target bits you need. Second, you perform your calculations, mentally or quickly on paper, running the logic operations. Finally, you draw evidence-based conclusions. For instance, if you apply an AND mask and the result is all zeros, you can't just stop there. You have to write down what those zeros mean in the actual context of the system being asked about. That is what we call actionable evidence, and that's what gets you the marks.
Moving right along to challenge 2, find the flaw. I want you to really think about this quote straight from a principal examiner report. Answers are not specific to the context given in the question. Look at the sample paragraph we are analyzing. It has perfectly accurate textbook-level computer science theory. But guess what? It loses major marks. Why? Because it completely lacks specific context. If the exam question is specifically about a temperature sensor's data register, your answer must explicitly mention that temperature sensor to secure full credit. You can't just talk about registers in the abstract. Connect the theory to the real-world scenario they gave you. Okay, here is your final workshop test. Challenge 3, the 30-second speed writing challenge. Put yourself in the exam hall. Imagine the exam is ending. You have one final 4-mark question asking you to justify the use of XOR in a simple encryption algorithm. The clock is ticking down. You need to execute your methodology like a flawless gymnast routine under immense pressure. Ready? Start with your point. XOR is used to toggle bits. Now your evidence. Applying a key bit of 1 to a data bit flips its value. Next, the explanation. This process is perfectly reversible, as applying the exact same key bit again toggles it right back to the original state. Finally, the link. Therefore, XOR provides a simple, symmetric method for encrypting and decrypting the data stream. Boom, 4 marks. Clean, structured, undeniable. That is the sheer power of practicing the Peel framework until it literally becomes muscle memory.
Section 4, critical warnings and the final system. Let's bring it all together.
We need to talk about the top 3 mistakes pulled directly from the examiner reports. Number 1, vague technical details. Just saying "and" makes things 0 is way too vague. You must be precise. Say something like, the AND operation with a bit mask of 0 forces the corresponding output bits to 0 regardless of the input state. Specificity is key. Number 2, ignored boundary conditions in edge cases. Listen to me, this is a fatal error in bit operations. What actually happens to the most significant bit during a logical shift versus an arithmetic shift before you apply an OR operation? Did you check what happens if the input is all 1s or all 0s? You must test the extremes. And number 3, lack of context, which we just tackled. I'll say it again, never write a generic answer for a highly specific scenario. To completely avoid those mistakes, you must consistently apply algorithmic thinking. Notice the workflow here. You have to decompose the problem step by step into its absolute smallest logical parts. Then, select the appropriate data structure. Next, implement efficient code with the exact right sequence of logic instructions. And finally, test rigorously against those tricky boundary conditions we just talked about. This process right here is exactly how you translate theoretical textbook knowledge into high-level, practical application skills. So, what does this all boil down to? It comes down to 3 overarching rules that guarantee top marks. Think of this as your complete cheat sheet recap for your exam system. Rule 1. Command word decoding. You must always know if you are being asked to describe, explain, or evaluate. Your entire structural approach hinges on that single word. Rule 2. Peel framework application. Never, ever write a massive wall of text again. Structure your logic tightly into point, evidence, explanation, and link. Rule 3. The time management matrix. Don't rush into a panic like Sam, and don't overwrite a novel like Alex. Allocate your time based strictly on the marks available, and trust the procedural framework you've practiced.
I want to leave you with this defining quote regarding higher-order assessment objectives from Cambridge. Top-scoring candidates demonstrate evaluative thinking by considering multiple solutions, analyzing trade-offs, and justifying decisions. This right here is the ultimate goal. When you are faced with a complex assembly language problem, don't just jump at the very first solution that pops into your head. Comparative analysis is required. Identify the similarities and the differences between using an OR mask versus an XOR mask in that specific scenario. Use comparative connectives. Analyze the trade-offs. Maybe one method takes fewer clock cycles, but maybe another uses fewer registers. Acknowledge the limitations of your approach and rigorously justify your final recommendation with hard, binary evidence. That is exactly how you secure an A-star. That is how you stick the landing. So the next time you look at a wall of 1s and 0s on your exam paper, I want you to remember the gymnast. It isn't just about memorizing logic gates, it's about executing a flawless logical routine. But consider this. As computing continues to abstract away from the hardware layer with advanced AI and high-level languages, why does Cambridge still rigorously test these fundamental bitwise operations? Perhaps it's because true masters of computer science aren't just basic operators of the machine, they are the architects of its deepest logic. Are you ready to stick the landing? Students who implement these computer science strategies see an average improvement of 2 grade boundaries, but that only happens if they practice consistently with our weekly explainer videos. Here's your final reminder. Subscribe to our YouTube channel Ace the Exams at acetheexams_IGCE to excel in your Cambridge examinations. Subscribe right now to acetheexams_IGCE and click that bell. Don't let another exam pass you by. Drop a comment below with your target grade for computer science and the biggest challenge you're facing. Our team responds to every comment. Like and share this explainer with a study partner. Ace the Exams. Your Cambridge success starts here.